Having that need to give some advanced material, and that by advanced material means that I will reach points where there are many difficulties, and therefore in a very short course I will not provide all the mathematical details. So I will try to forward some philosophical view about that. But anyway, I find a few simple problems that are instructive enough so I can forward that information. And the guiding lines will be at the same time, because we are all interested by applications, will be to use mass transport or heat transport as a generic problem. So the lecture is organized like that. There are some short introduction, but mainly it has been covered by Professor Pillay. Then I will discuss a little bit the general framework for upscaling based on a simple definitive problem, and then I will use that for the mass transport case, because we know we need to at least have heard one time about dispersion. And then I will use the heat transfer problem to go to review many different models that we can develop based on a simple problem. There is one of the important messages I will try to forward today is that I have a power scale problem where there are not necessarily a single macroscale model. There are many models, and those models depend on actually the way the different physical properties and geometrical properties of the problem are organized in the system. So I will not redo that now right now, just to gain some time. So the introduction was essentially done by Professor Pillay. So our objective is to smooth a power scale situation into a microscale modeling, and this requires several things. So first, to define macroscale quantity based on power scale definitions, and this has been introduced by Professor Pillay in terms of averaging operator. There are other proposals in the literature, but we will use that today. And we want also to find macroscale equations, and Professor Pillay has illustrated how we can obtain that in the case of Stokes problem. We already had a side discussion about the effective boundary conditions. I will not talk about that today, but this is a very important problem, because I cannot solve a macroscale problem if I have no effective boundary conditions, but I'm not going to discuss that. We have introduced all notations for the averaging operator, so no need to waste time again. We also have introduced the scale separation assumption, which is also something very important. And I just would like to remind you that this is not always the case. There are many systems for which there are continuous evolving heterogeneities, for instance, so this is not the case. The averaging theorems they have been introduced by Professor Pillay, so I will not comment that. And we already discussed the approximations that we will use. So I just would like to remind you that averages will be extracted from averaging operators, and that's something. And that also we will use this approximation, which is actually connected to this one, and that the average of deviation is 0. And something very important, the average of a flux involving a gradient of temperature or concentration will be written in terms of some sort of macroscale flux here, a simple, plus a correction which depends on the tortuosity of the system, and this approximation has been discussed 1 hour ago. So this is the starting point. Let us review the idea of upscaling based on a very simple problem. Let us take something very simple. I will take a diffusion equation where the diffusion coefficient is just a smooth function of the variable, the space variable. So very simple. And the idea put forth for the Darcy problem by Professor Pillay is just to solve this problem in terms of decomposition with an average value and a deviation. So what do? We have a small scale field here, the red line, which has some oscillations which are related to the pole scale characteristic length, and then obviously an average signal. And so we want to replace that by the coupled problem with the average signal and the fluctuation. So typically, this looks interesting because here we see that we sort of recover some sort of oscillations, a local periodicity of the system, which is an interesting thing. And if I do that, if I inject that decomposition here, I first get a very simple equation here, and another equation for the deviation. So we have a couple problem here, and on the next slide I'll just go through the mathematics in a quite straightforward manner. So let us take the average of the balance equation. That's very important. Since everything is smooth here, this is simple. I have the divergence of the average, and if I introduce the decompositions, I get this macro scale or would-be macro scale equation in which I have the gradient of the average temperature, and here some term involving the deviation. So this is not yet in a closed form. To get a closed form, I need the governing equation for the deviation. So the governing equation is just a small scale equation that I will rewrite using the decomposition. So the pole scale equation is just that. And well, I am tempted to try to simplify that by using this equation. So if I subtract this equation to this one, I get an equation like that, which in the end gives a governing equation for the deviation. So I have a diffusion term here with the temperature deviation. I have an integral term here, and I have a source that depends on two things. It depends, of course, on the heterogeneities, the variations of the diffusion coefficients, and it depends on the large scale gradient. So if I come back here, in places where there is no gradient, deviation is 0, and the fluctuation here is larger where I have a steep gradient. That's a very nice feature because I have a linear, I have two coupled equations with a linear here relationship. A term involving the temperature, the gradient of the average temperature, and this suggests to introduce some approximate solution of this coupled problem, and the approximated solution is actually what is called the closure. So the closure is not something that just pops up because I want to have a closure. The closure must be associated to the mathematical structure of the coupled problem that you are working on. And that's very important. And that's why linear problem, it looks easy. If it is nonlinear, this is a little bit more involved. I will not develop things today, but this can be done. So if I introduce a linear relationship, and then introduce that in the governing equation here, I get a governing equation for this mapping vector, and the governing equation is just a diffusion equation for this mapping vector, and a source term which is the divergence of the fluctuation of the diffusivity. So what triggers some pulse media effect is just the fluctuation of the transport properties. This comes from the fact that the average of that is 0, and then Professor Pillai has added some additional things which are most of the time periodicity conditions, but I have a slide on to discuss that particular thing. Once I have got that, I can introduce that in the average of the polar scale equations, and I get the macro scale equation here, in which Kf is just the average of the diffusion tensor plus this correction term here that comes from the mapping between the temperature deviation and the gradient of the temperature. So that's the something that will be repeated many times. It's simpler here because I have taken a smooth field K. It turns out that if you define all this in the sense of generalized function or distribution theory, it also works for a piecewise conductivity. But most people are not familiar with distribution theory, so I'm not going to use that here. And this is the way it can be used has been already illustrated by Professor Pillai. So you have to get some sort of data, X-ray topography, NMR, whatever. You solve for the mapping quantities, and you get what you want, your effective property. Well, it's not that straightforward. The use of periodicity condition is very powerful. Let us take an example. This unit cell looks bizarre, but actually this is a unit cell for a stratified medium. So all kind of geometrical orientations, anisotropy, etc., will be solved in a very straightforward manner if you have a periodic system. You don't mind about it. And if you introduce a unit cell like that in the closure problem, you will get your effective tensor, which is something a little bit complicated, but involving the vector orienting the stratified system. Well, so that looks very powerful. No problem with anisotropy. Well, but what if I have an image of a medium